So let us see a very simple example. Consider hydrogen molecule. Again, it's a 2-electron system. So we know that for H2, you will have a sigma orbital and sigma star orbital. And these are actually the spatial orbital, or they are the spatial functions. Then the ground state, of course, is at the equilibrium geometry of H2, then the ground state is sigma 2, right? So this is the ground state electron configuration. So this is equivalent to say I have sigma 1, alpha 1, and sigma 1, beta 1, sigma 2, beta 2. Right? So this is phi 1, x1. This is the spin orbital for this first electron. This is the spin orbital for the second electron, right? And the corresponding Slater determinant is 1 over square root of 2, sigma 1, alpha 1, sigma 2, beta 2, and sigma 2, alpha 2, sigma 1, beta 1. Right? So here I simply use 1 and 2 to denote for R1, R2, or S1, S2. So here, for the spatial function, this 1 simply means R1. 2 simply means R2. For the spin function, 1 simply means S1. 2 simply means S2. Okay. And if we consider an excited state, suppose we have 1 electron up and 1 electron down, sigma, sigma star. Then of course you have sigma 1, alpha 1, sigma star 2, beta 2, right? This is 1 over square root of 2, sigma 1, alpha 1, sigma star 2, beta 2. And this is sigma 2, alpha 2, this is sigma star 1, beta 1. Okay. Now, of course, you can also write down, for instance, what is the Slater determinant for the ground state of lithium atom. In this case, you will have 3 electrons, right? So you will have a 3 by 3 determinant. All right. So I have several remarks. So first of all, a single Slater determinant is an eigenfunction of Sz. This Sz, of course, is the total Sz. This is the total, this is the projection of the total spin angular momentum along the z-axis. This is equal to the summation of Szy. So if you apply Sz on a Slater determinant, you will have 1 over 2 n alpha minus n beta times Slater determinant. So n alpha is the number of alpha electron in your system, and beta is the number of beta electron in your system, and this is equal to capital MS. This is the total MS, SD. Okay, this is very easy to prove actually, because, well, for alpha electron, you have positive 1 over 2. For beta electron, you have negative 1 over 2. Of course, this is in atomic unit. I simply let h bar be equal to 1. Okay. And another concept is called spin multiplicity. This is 2s plus 1. Here, this s, capital S here, is the total spin quantum number. Okay, so to compute the total spin quantum number, first you need to apply the total spin angular momentum operator, actually the square of the total angular spin operator, onto the Slater determinant. And if you have an eigenfunction, if the Slater determinant is an eigenfunction of s squared, then you can rewrite the corresponding eigenvalue as s times s plus 1. And this s is the total spin quantum number. However, a single Slater determinant actually may not be an eigenfunction of s squared. This is very important. So if you have, say, so the orbital is either empty or it's doubly occupied, then this is the so-called closed shell configuration. Or if we have, so this is a pi electron orbital for a benzene ring, right? So this is also closed shell. Then for this case, the Slater determinant, the single Slater determinant correspond to the electronic configuration is indeed an eigenfunction of s squared. So s squared applied s squared on the Slater determinant, you will get 0. That means the spin quantum number is 0, or you can say the magnitude of the spin angular momentum is 0. And this is the so-called singlet, because 2s plus 1 is equal to 2 times 0 plus 1 is equal to 1. And this is called the singlet state. On the other hand, if we consider, say, all singly occupied orbitals have the same spin, then this is actually the so-called high spin state. And for high spin state, the Slater determinant is also an eigenfunction of s squared. In particular, for this case, if you have 2 electrons, you will have s squared x on a Slater determinant is equal to 2 h bar squared Slater determinant. So in this case, s plus 1 is equal to 2, then s is equal to 1. That means the spin quantum number is equal to 1. And therefore, 2s plus 1 is equal to 3. And this is called a triplet. Okay. Well, if you don't have closed shell configuration in which all the electrons are paired with each other, or you don't have high spin state in which all singly occupied orbitals have the same spin, then this later determinant is usually not an eigenfunction of S squared. For instance, if you consider one up, one down. This is definitely not closed shell, and this is not high spin state. This is actually an intermediate spin state, because, well, you have two singly occupied orbitals, but one is in alpha state, another one is in beta state. So in general, this kind of electronic configuration, or this kind of the corresponding Slater determinant, are not S squared eigenfunction. Another way to say that is this Slater determinant or this electronic configurations are not spin eigenfunction. Of course, it's an eigenfunction for Sz, the projected spin, but it's not the eigenfunction for S squared. Okay, it's actually very easy to validate that. You can simply write down the corresponding Slater determinant and it will apply S squared on this Slater determinant. Let's see whether or not you can find an eigenvalue. You cannot do that actually. All right, I will leave this simple derivation to you. Okay. Now, if our total Hamiltonian does not contain S, that is to say, spin is not part of the Hamiltonian. So usually that means we ignore the spin-orbit coupling. Because the spin-orbit coupling operator is actually a product of the angular momentum and the spin momentum, and spin angular momentum. And if you include this term in your H, then the system becomes somewhat complicated. But if we don't consider that term, then it's easy to show that H and S squared, or H and Sz, they commute with each other. Okay? That means, if you remember our previous lecture, that means there must exist a set of common eigenfunctions of H, S squared, and Sz. Okay? So we denote this set of common eigenfunction as phi. Of course, it's a function of the complete electronic coordinate from x1 to xn. And it's not going to be, in general, a single Slater determinant. Because, for instance, for this up-down, one up and one down configuration, this is not a spin eigenfunction. So, in general, this set of common eigenfunctions, which are this eigenfunction of spin, is going to be a linear combination of Slater determinant. And each Slater determinant as the k correspond to a particular arrangement of the electronic configuration. So this is the so-called spin adapted configuration. This phi, this linear combination, which is an eigenfunction of S squared, is called spin adapted configuration. or you can call them as configuration state functions. Configuration state functions are, of course, spin eigenfunctions. So if you want your system wave function possess good property, for instance, for the spin, then you should work with the configuration state function. So for the example we have mentioned previously, if we have one down, one up, right? You can have a particular Slater determinant. And of course, this is not the spin eigenfunction. But you can also look at one down, one up, right? And this is another Slater determinant, right? This is spatial orbital A, this is spatial orbital B. And SD2, of course, itself is not a spin eigenfunction either. However, if you combine SD1 and SD2, you can form a spin eigenfunction. In particular, if you do 1 over square root 2 SD1 minus SD2. You do this linear combination, it turns out that if you apply S squared on this configuration state function, you will get 0. So this is, this phi is a spin eigenfunction. In particular, it gives you a singlet state. If you do 1 over square root 2 SD1 plus SD2, and then you apply S squared on phi, you will get 2h bar squared phi. Here I just write 2 phi again. I'm using atomic units. So h bar is 1. So 2h bar squared is 2. And therefore S, the spin quantum number, is 1. And this gives you a triplet. So you cannot say this gives you singlet, or you cannot say this gives you triplet, because it's an illegal question, right? It's not eigenfunction. You cannot talk about what is the spin quantum number. Of course, you can calculate the expectation value of the spin, no problem, but you don't have a spin eigenfunction here. So you cannot, it's illegal to say SD1 is a singlet or SD1 is a triplet. That's illegal. However, if you do a linear combination, you can say this particular combination is a singlet, or this particular combination is a triplet. Okay. So I should also say that phi, this configuration state function, is not in general the total many-body wave function for a system. Okay, because it only represents a particular arrangement of the electrons on the spatial orbital. So for some system, the total wave function in general actually is a linear combination of all the possible arrangement of the electrons on the spatial orbital. So phi, or this configuration state function, should be I should say it should be understood as a linear combination of Slater determinants that correspond to the configurations with the same electronic occupation for spatial orbitals, but different occupation for spin orbitals. That's the way to understand this linear combination. That's the interpretation of the configuration state function. And of course, if you have, say, n electrons, and you have this kind of intermediate spin state, how to construct this linear combination? You need CK, right? CK actually is completely determined by the angular momentum coupling method. So actually it's fixed. It's a fixed value. Its role is actually the Clebsch-Gordon coefficient, right? If you remember what we talked about in the previous lecture, when we talk about the addition of angular momentum, we introduced a set of Clebsch-Gordon coefficient, right? So CK here, all of those CKs have the same role as the Clebsch-Gordon coefficient. And they can be determined by a standard procedure. This procedure is called genealogical coupling scheme. You can refer to the related reference for this scheme. I will not talk about the detail of this scheme. You simply need to know that, well, this is a standard procedure given, say, 5 electron or 10 electron, whatever, given n electron. And if you have an intermediate spin state, you can systematically use this scheme to determine the value of CK, so that you can use this set of CK to construct your configuration state function. And you can construct the configuration state function that corresponds to a particular spin state. Okay. So the last topic we will talk about in this lecture is the so-called Fermi hole or Fermi correlation. Again, let's look at independent two-particle wave function. Suppose you have an electron occupying phi A orbital, another electron occupying phi B orbital. By the way, phi A and phi B, of course, are two different, or they can be two different spatial orbitals. And if you only consider a pair of electrons that occupy exactly the same spatial orbital, this and this are not necessarily degenerate, okay? If you apply an external magnetic field, you can distinguish different spin, okay? You can distinguish between different microstate given a particular spin multiplicity. For instance, if you have a triplet state, you will have 3 microstates, okay? If you look at the energy without external magnetic field, they are the same, but they are 3 different states. If you apply an external bias, for instance, an external magnetic field along a particular direction, then this 3 microstate will have different energies. Okay, so of course, this phi x1, x2 is described by a Slater determinant. Now, let's consider the probability distribution. This is, of course, 1 over 2, and the solidity determinant. Now we can do a expansion for this 2 by 2 solidity determinant. This is easy enough. Psi A, 1, alpha 1, psi B, 2, beta 2, minus psi A, 2, alpha 2, psi B, 1, beta 1, squared dx1, dx2. Right? So what is the probability of finding electron 1 being in the R1, or electron 1 at point R1, and electron 2 being in the R2, electron 2 being at point R2. So this is the probability that in the real space, right? This is a spatial probability, spatial distribution. Probability R1, R2, dR1, dR2 is, of course, the integral of phi squared ds1, ds2, dr1, dr2. Now, this integral is over the spin coordinate. This integral is over the spin coordinate. If you integrate over the spin coordinate, what's left, of course, is the probability distribution in the three-dimensional space, right? Now we need to do a little bit of algebra. This is 1 over 2 integral psi b 2 squared alpha star 1. Now, you have the magnitude here, right? This is magnitude squared, and this is equal to phi star times phi. Keep in mind, this is phi star times phi, okay? So you will have alpha star times alpha, beta star times beta, ds1, ds2. Okay, this is the first term. We will have we will have 4 terms, right? Because you have phi star times phi, and phi contains 2 terms. So phi star times phi contains 4 terms. So this is the first term. What's the next term? Psi A 2 squared, psi B 1 squared, alpha star 2, alpha 2, beta star 1, beta 1, ds1, ds2, right? The second terms come from exchanging the label of 1 and 2, right? The first term is psi A1 squared, psi B2 squared. And when you change the label, when you exchange the label between electron 1 and electron 2, you have psi A2 squared times psi B1 squared, right? Similarly, for the spin part, you have alpha star 1, alpha 1, beta star 2, beta 2 in the first term. For the second term, you have alpha star 2, alpha 2, beta star 1, beta 1. Okay. Now, what's left is, of course, the crossing term, right? You will have 2 crossing terms. This is a pretty long term. So you will have crossing term. That means you will have electron 1 in orbital A, electron 2 in orbital A. in one product, right? And another product will be electron 2 in orbital A and electron 1 in orbital A. That's in another product, right? So you will have posi A star 1, posi B star 2, posi A 2, posi B 1, plus an antisymmetric term 2, 1, 1, 2. And the spin part is alpha star 1, beta star 2, alpha 2, beta 1, ds1, ds2. Okay. And don't forget dr1, dr2. Okay? Because you see here, we're first integrating over the spin coordinate, then don't forget to multiply by the volume element. So here we have the volume element. Okay. Now, this, of course, gives you 1, right? You integrate the first electronic spin coordinate. You have alpha star 1, alpha 1, of course, this is normalized. This is 1. This is 1. This is also 1. And alpha 1 star times alpha 2, times beta 1, ds1, right? Gives you 0, right? Because for an electron, the alpha and the beta states are orthogonal. Similarly, for electron 2, beta and alpha are orthogonal. You get there. So really, you don't have the second term. You don't have, you don't have the crossing term, right? You don't have the third and fourth term. They're the crossing term. Because the spin states are orthogonal. The alpha and the beta are orthogonal, so that you don't have the crossing term here. So in the end, you simply have 1/2 posi A 1 squared posi B 2 squared plus posi A 2 squared posi B 1 squared. That's it. What is this term? This is the probability for the electron 1 occupying orbital A being in dr1, right? This is the probability of electron 1 occupying orbital A being in dr1, right? What is this term? This term is electron 2 occupying orbital B being in dr2, right? What is this term? This term comes from the exchange of the labels, right? So you see, if you just look at the first term here, you can say that the first electron and the second electron are completely independent, right? That is why when we have, remember, we start from anti-parallel spin, right? We have one up and one down. We have a pair of anti-parallel spin electrons. So in this case, the probability for E1 in dr1 and E2 in DR2 is equal to an average, right? You have 1/2. That is the average of the probability of E1 in orbital A being in DR1 times the probability of electron 2 in orbital B being in DR2 plus the probability of electron 2 in orbital A. Now you're exchanging the label for the electrons, right? So E2 in orbital A being in DR2 times the probability of E1 in orbital A being in DR1, right? So, well, it's this probability for electron in DR1, electron 2 in DR2 is simply a product of electron 1 in DR1 and electron 2 in DR2. So it's really independent, right? So the motion of two anti-parallel spin electrons, one up, one down, is uncorrelated. That means they are entirely independent. As described by single Slater determinant. This is very important. If you choose to use a single Slater determinant to describe a pair of anti-parallel spin electrons, then their motions are completely independent. They are not correlated with each other. Now, let's consider a pair of electrons that have the same spin. Let's consider, for side A, you have an alpha electron. On side B, you have another alpha electron. Okay? So phi, this is the Slater determinant, is what? 1 over square root 2 for side A, 1, alpha 1. For side B, 2, alpha 2. For side A, 2, alpha 2. For side B, 2, alpha, for side B, 1, alpha 1, right? Again, probability R1, R2, dr1, dr2 is equal to what? This is again equal to, you do the integral of phi over the spin coordinate, dr1, dr2, right? You do the integral over the spin coordinate, so you have the distribution in the three-dimensional space. And again, you have, let's do this expansion. 1 over 2, you have cosine A 1 squared, cosine B 2 squared, alpha star 1, alpha 1, alpha star 2, alpha 2, ds1, ds2. That's the first term. The second term is integral psi a 2 squared psi b 1 squared, right? You're exchanging the labels here. Alpha star 2, alpha 2, alpha star 1, alpha 1, ds1, ds2. Now, the crossing term, integral psi a star 1, psi b star 2, psi a 2, psi b 1, plus psi a star 2, psi b star 1, psi a 1, psi b 2, alpha star 1, alpha star 2, alpha 2, alpha 1, ds1, ds2, and finally dr1, dr2. All right. Again, this gives you 1. This is 1, 1, 1. And this also gives you 1. You see, here we don't have a orthogonal property here because we're considering both alpha electrons. So alpha star 1, alpha 1 gives you 1. And here alpha star 2, alpha 2 also gives you 1. This is where the difference comes from, right? When we have a pair of antiparallel electrons, this term, you will have alpha 1, beta 1, right? But when you have a pair of the same electrons, the same spin electrons, you don't have 0. You have 1 here, right? Because you have alpha 1, alpha 1. And for the second electron, you have alpha 2, alpha 2, right? So that means you have 1 over 2 psi a1 squared psi b2 squared plus right? Minus a term, right? Minus the crossing term. Right? So the first two term, again, this is the average of the independent probability distribution. But now you need to minus a term, minus a positive term. This is the correlated term, right? So now the probability is smaller than the two completely independent electrons, right? So the conclusion we have here is that the motion of two parallel spin electrons, they have the same spin. They're all up, up, or they can be all down. So in this case, they are correlated. Right? That means the probability for finding electron 1 at R1, electron 2 at R2 depends on the other electron. So the probability of finding a particular electron depends on the other electron. So these two electrons are, of course, treated as independent. In this sense, independent means you ignore the Coulomb repulsion between these two electrons. However, their motion are not entirely irrelevant. Their motions are correlated. Right? So this probability is smaller than when you have one up, one down. Right? This is truly uncorrelated. When you have one up and one down, the probability is truly uncorrelated. The motion of these two electrons are truly uncorrelated, independent. Right? But now we have a smaller probability. That means the two parallel spin electrons are avoiding each other. Right? Intrinsically. This is important. This is the intrinsic property of the electron. If the electron carries zero charge, well, or I should say, let's just consider two neutral particles without any electric charge. They're neutral. However, if these two particles, they have spin 1/2, and they have one alpha state and one beta state. If you consider two alpha particles, okay, two particles with the alpha state, with the alpha spin state, they will avoid each other. This is something intrinsic. This is not due to the Coulomb repulsion. I need to emphasize this because, of course, two electrons will avoid each other because they carry the same charge, right? Two negative charge avoid each other. But this is because of the Coulomb repulsion. What we're talking about here is that if you remove the charge carried by the electron, if the electrons are neutral, they still avoid each other when you consider two alpha spin electrons or two beta spin electrons. So this is something fundamentally different in classical mechanics. In classical mechanics, you don't have this. This is a fundamental quantum mechanical phenomenon, okay? So this kind of correlation or this kind of repulsion, this kind of repulsion is not electrostatic. This is fundamental due to the spin, okay? This kind of repulsion is called polyrepulsion. This kind of correlation is called Fermi correlation. You are still considering independent electrons. They do not interact. Okay? They do not interact. You ignore the Coulomb repulsion. However, their motions are still correlated. This is called Fermi correlation. Another way to say this is that there exists a Fermi hole around an electron. So intrinsically, another electron with the same spin cannot get very close to this electron if they have the same spin. So intrinsically, they are avoiding each other, okay? So if you, let's say if you, so if you draw a picture, so you have one alpha electron, you have another alpha electron, or you have a beta electron, you have another beta electron, you have a pair of parallel spin electrons. Then if we use the green shadow to represent the probability distribution, now of course, you will see a hole around an electron. So within this region, the probability of finding another electron is extremely small, okay? On the other hand, if you consider, say, one up and one down, and the probability distribution can be drawn as okay? They're entirely independent. They can move, the up spin electron can move anywhere, okay? The spin down electron can move to anywhere, okay? They're purely independent if you ignore the Coulomb repulsion, okay? This is also important. If you ignore the Coulomb repulsion, in other words, you're doing this independent, non-interacting model, then the probability for finding electron 1 at R1 and for finding the electron 2 at R2 is simply an average of the two product term, okay? So the motion of alpha and beta electrons are uncorrelated. These motions are uncorrelated. They're entirely independent. So we should say that a Slater determinant has incorporated Fermi correlation between alpha alpha or beta beta electron, spin parallel electron. Okay. However, for a pair of up down electron, the motion are not correlated. Okay. This is, of course, for single Slater determinant. Our discussions are based on single determinant.